function is to determine end behavior, and that's our goal, all right? So when you look at to determine end behavior, you want to look at the leading terms. So the leading terms here is x squared, and then the one on the denominator is x. So if I were to simplify that, I'll get x, which is a linear expression. And therefore, you know you're going to get a slant asymptote. Are we good? We went over this, I think, the last time we meet. We then use long division to divide to get our linear expression, because that linear expression is the slant asymptote that we have. We know how to graph this line. This line has a positive slope, so your line is going to be increasing. Now, the end behavior of this line is going to be the same as the end behavior of this rational function. And that's why we want to use that, so that we use what we know to find out the function that we don't know, okay? So when we graph, and notice I sort of print out the graph for you, you're going to see that the end behavior of this rational function, which is in red, is the same as the end behavior of your slant asymptote, or the quotient that you use the leading term to find. So now what we're going to do is we're going to write our verbose sentence, okay? It says, as input of value of f of x increase without bounds, so that means x, that's your input is x, increase without bound mean x go to infinity, x approach infinity. My output value, that's my y, okay? Now understand that when x approach infinity, we're looking at the right end. Okay, so I want to know, well, what happened on the right? Now, if I don't have the graph, then I need to look at my function right here, or the quotient. It doesn't matter which end you use, okay, or which one you use. In this case, if I'm using this one, I can see that as x approach infinity, my function, which is the rational function, will have that same end behavior, which means the y value will approach infinity as well. So I'm going to write output value of f of x, yeah, bless you, increase without bounds. Again, why? Well, because your y is going up. Going up means increasing, or going to infinity. I want to write the limit notation, so let's write that. This is the limit. We write your x right underneath it, go to infinity. Then you got to write your function. The name of your function is f of x. If f of x increase without bounds, that means your function goes to infinity, or go up. In plain term, as x move right, your function move up. That's what it means, okay? All right, we're going to do the next one. And this is where I asked you guys to change this to decrease, right? Input values of f of x decrease without bounds. That means x goes to negative infinity. And as x go negative, we're talking about the left end, okay? So that's why we call this the left end behavior, and then the other one is the right end behavior. We want to know, well, what is your output value doing? Well, as x decrease without bounds, because this is a line, on this end, the line is going to go down. That means your function is approaching negative infinity. In other words, decrease without bounds. Yes? So we're going to write value of f of x decreases, or decrease, without bounds. This means f of x, right, go to a negative infinity. And that's what we see here for our slant asymptote. So we're going to write our limits right here. The limit as x approach negative infinity. The name of your function is f of x. Your function is decreasing. That means your y is going to negative infinity. Questions on that? Are we okay? Again, it does show that on the graph. The idea is, what if I take away the graph? how can you find this? And that's what you're going to do on the AP exam. Okay? Any question on this one? Can I move on? Okay. Let's move on to example 2. Now, I want, again, given this function g, determine the end behavior using limit notation. I gave you the answer here. Hopefully you can see that. Here's your answer. This is your graph. You guys see that? Now we can see the end behavior of the graph already. So this end, you can see the function is going up. And this is my right end. You see that? And here's my left end. On my left end, the function is decreasing. So that means the function y is going to negative infinity. We can see that. Is that good? The question now is, what if I take away the graph? Now, how can I still find that? By looking at the function itself. You guys see that? Okay, so this is what you're going to do. You're going to look at the leading terms. Ms. Tran, when we look at end behavior, do we always look at leading terms? Yes, if this is a rational function. Okay, so look at the leading terms. Oh, it's also true for polynomial. My leading term for the numerator is x to the 5th. Because that is the term with the highest exponent. The term with the highest exponent on the numerator, on the denominator, is x squared. So that's my leading term for the denominator. Now, if I simplify this, I will get x cubed. You guys good? Now, this is what I know. I know this is a cubic function. So in the past, I have learned that cubic function looks like this. So this is x cubed. Are you guys good? Now, this is what I care about. I care about the end behavior of that x cubed function. Because this end behavior is going to be the same end behavior as that of the rational function g. Are you guys good? And if you look at the answer, do you guys see that the end behavior are exactly the same? That's why we don't need this graph anymore. If we can simplify into a function that we know, then we can tell the end behavior of this function that we don't know. Does that make sense? Okay. So now, what do I know? Well, I know this. This is my right end. Right? It's on the right. So this is my right end. And the right end means x is approaching infinity. And if you take a look, you can see that your function, right, is increasing as well. That means your function is going to infinity as well. Do you guys see that? Yes? So this is my true function. This is the true function. This is the function where the end behaviors is the same as my true function. Right? This one is the left end. So we're going to write left end right here. Right, this is the one on the left, and this is where x approaching negative infinity, right? So we want to know, well, where does f of x approach to? Oh, in this case, my bad, it's not f, it's g. Let's change this to g. Whew. Right, the name of the function is g. Let's change it to g. Well, g of x, the function is decreasing. That means g of x go to negative infinity as well. Now, we're going to put this in the verbal sentence, and then we're going to write our limit notation, okay? Why don't you try this out? As input value of g of x increase without bounds, what is your output value of g of x doing? So go ahead and write that, and see if you can write your limit notation for me. Go ahead and do that, please. I'll give you some time to do that. All right, you guys got it? Let me double check your work, yeah? As input value of g of x increases without bounds, so this translates to x go to infinity. Your output value, which is your y, output value of g of x, well, this n, the function is increasing, so the output value of g of x increase without bounds. My limit should be lim, x got to go to infinity. So it has to be right underneath the lim, okay? And then the name of your function is g of x, that's the y. Y go to infinity. We good? What I want you to be familiar with is the language, because they're going to use that on the multiple choice, okay? Next one. Input value of g of x decrease without bounds. That means x approach negative infinity. So therefore, your output value of g of x, and let's see where it goes. So as x go to negative, the function also go down. That means decrease without bounds. Your limit should be the limit as x approach negative infinity, g of x also go to negative infinity. Is that good? Any questions? Okay, now we're going to have to do one where it doesn't do this. You guys good? So I need you to go to the next page. Let's move to the next page. All right, let's take a look at this problem. Go ahead and read this. You're going to see the answer right here already. I hope you see it. But we're going to have to imagine taking that away and find our end behavior. You guys good? So go ahead and take a look, please. So it says, given h of x. Ah, man, change this to h of x for me. It has to say h, because the name of the function is h. Okay? All right, given h of x, which is this rational function, I want to determine the end behavior using limit notation. Now, if you look at your answer, you're going to see that the right end, which is this end right here, bless you, you guys see that the right end, it doesn't go to infinity anymore, but it's flat now and it's approaching the x-axis, which is where y is 0. Do you guys see that? So now we have to change our language because it doesn't go to infinity anymore. And as you look on the left, as x approach negative infinity, which is the left end, you're going to see that your function flat now, and it is approaching, again, the x-axis, which is y equal to 0. You guys see that? So now, if I take this graph away, I want to know, how do I find that on my function itself? Okay? Again, you're going to look at leading terms. So go ahead and write leading term for me. I'm going to use black because I think this one is easier to read. Okay, we're going to look at the leading terms. My leading term is 2x, and then on the denominator is 3x squared. If I simplify this quotient, I will get 2 over 3x. Everybody okay with that? Yes? Now, recall, end behavior, that's when x is approaching infinity or negative infinity, which is a large value. You guys see that? So if I plug in a large value for x, what I will get is a situation of a small value divided by a large value. And that means my answer is going to be 0. Let me give you one example. We have about 1,300 students in this school. Okay? Let's say I have $1. And I want to divide that evenly to 1,300 students. That means each student is going to get $0. Nothing. Not even a cent. Do you guys see that? So a small value, when you divide it by a large value, So keep that in mind. You're going to get 0. Your value, your answer is going to approach 0. That's what we're saying. And if you have a number, once you simplify the leading terms, this means you have a horizontal asymptote. Okay? So it's either a 0 or an actual number. So here in this case, you have a 0, so your horizontal asymptote is y equal to 0. And that's what you see right here. You see a horizontal asymptote. Y equal to 0. Is that good? Now, what if you like Ms. Tran, but in the other problem, you gave me something like this, and you tell me the end behavior, right? How come I don't have that here? Well, if you want, you can look at it, because 0 means you have a horizontal line where y is 0. Do you guys see that? So if I look at the end behavior of a horizontal line where y is 0, then I can see that this end, the function is going to approach 0. On the right end, the function will approach also 0. You guys see that? That's what it means to be a horizontal asymptote. Your y is going to this number. So the way we write it is this. As input value of h of x increases without bounds, and again, that means x go to infinity. X move right. So we're talking about the right end again. Your output value of h of x, and this is the language that they're going to use in your homework and on the test. The output value approach. Okay? Or they're going to say get arbitrarily. Oh, cannot spell arbitrarily. Hold on. Okay, get arbitrarily close to 0. So your output value of h of x approach 0, or they can say the output value of h of x get arbitrarily close to 0. So it's going to get very close to 0, but it doesn't touch 0. Are we all right? So how do you write your limit notation? Well, here's how you write it. LIM, limit, x approach infinity. The name of your function is h of x, and h of x is approaching 0. So you write 0. Is that good? But this is what I want you to know. When you see this, you have to know right away. That tells you you have a horizontal asymptote. They will not say it. You have to recognize it. Okay? That's what this means. Are we all right? Let's move on to the next one. As input value of h of x decrease without bounds, that means x approach negative infinity. Again, we're talking about the left end. Output value of h of x approach, or they're going to say get arbitrarily close to 0. So if I were to write the limit notation, this would say limit as x approach negative infinity of h of x. So as x go to negative infinity, h of x go to 0. Any questions so far? It's heavy language base, I get that. But hopefully you get used to seeing these things. Okay? Can we move on to the next one? We have one last one, and I think we're done. You can see the answer here. You see that I have a horizontal asymptote, because as you look on the left end right here, you guys see that your function is approaching, it's flat out, and it's approaching 2. You guys see that? Same thing on the left, this left end. On the left end, your function is flat out, and it's approaching 2 again. So you do have that horizontal asymptote. Which is y equal to 2. We see it on the graph. Now, one more thing. I want to show you this one. When you look at this, a lot of students look at me and ask me and said, Ms. Tran, that's not true. This thing go down. So isn't that true that this function is approaching negative infinity here? That is true. But you guys see that this function is approaching negative infinity when x is around -1? You guys see that? Right? Here's -1 right here. Right? Right there. Your function is approaching negative infinity around -1. But what I'm asking you is, what happens as x approaches negative infinity? So as x get larger and get more and more negative, then I don't look at this one, I have to look at this piece. You guys see that? So you gotta be very careful which one you looked at. And that's why I keep saying left end and right end. Look at the one further left and further right. So don't look at the one in the middle. Look at the one further left and further right. Are we good? Okay. So I know this. I have a horizontal asymptote at y equal to 2. Now, I need to see that in my equation. So one more time. I need you to find me the leading terms and divide that, please. Okay, you try that. Go ahead. So hopefully if you look at your leading terms, 2x squared divided by x squared, you get a 2. Yes? That 2 represents your horizontal asymptote. Y equal to 2. All right? So now we're going to use our language to write our sentence. Go ahead and write it, and write me the limit notation as well. Go ahead and do that. Bless you. Go ahead and write the sentence frame and then the limit notation. Bless you. So take a look at the very first one. Do you have something like that? As input value of g of x increases without bounds, output values of g of x approach or get arbitrarily close to 2. And then here's your limit notation. The limit as x approach infinity of g of x is 2. And again, understand, whenever you see this, this tells you horizontal asymptote. Okay? Make sure you know that. This one, I'll write that and then you check. Okay, so you write yours and then look up and check with mine. So what I have is, same thing, but this time x is approaching negative infinity. And then g of x is approaching 2. Questions on this? Okay, we're done.